Hello everyone. So in this video we will be looking at a journey of an IO. So what happens when you do a read or write system call over a file, whether it has a file system on it or not, the layers that it goes through, and the different variations that you can have while doing the open and the write system calls, and how that affects the code path and the significance and the importance of all of them. So, without any more delay, let's dig in. Right, so the agenda for this video is first we're gonna describe what an IO device is. It may sound like a simple question, but for an IO device, uh, when you're describing an IO device, the direction is involved, right? Whether the signal is where it is originating, who's sending the signal to, for whom it is meant for, and when direction is involved, there is need to establish perspective. So we will have some more details describing what an IO device is. Then we're gonna pick an IO device for this videos, and that would be block device. Next, what we're gonna do is for every IO there's a beginning, and we're gonna have a very simple C program in which we're gonna open a file and do a write system call where describing the point where that IO would begin. And then what we're gonna do is we're gonna look into the various layers one by one through which that particular IO would go through, starting from the exact system call that is made in the sample C program, going to the VFS layer, which is the virtual file system layer. We're gonna then look into some of the variations on the open and write system call and how it affects different paths that your IO takes. Then next what we're gonna do is we are gonna look into the bio layer, which is the block IO layer, and the multi-queue block layer. In this particular presentation, we would not delve into a lot more detail into the multi-queue block layer and the bio layer. We're gonna have another session where we're gonna do that. Next, we're going to look into one of the device drivers and how it handles the I/O when it's handed to it, right? So let's begin. So as I mentioned, what is an output device, input-output device, right? And as I described, there's a direction involved in this description, and when there's direction involved, there's always a need to establish perspective when you define define something for it. And it could be, I mean, for this concept, there's a user involved, there's a computer system involved, and an input device is basically an output device for the other. And for this presentation, what we're gonna do is use we're gonna take the user's perspective in this definition, uh, and sticking to the basic description. Uh, a user sending a signal to the computer system through a device, then that device is an input device. Conversely, a device through which the computer system can send a signal to the user, and that is what is an output device, right? And even when we establish this perspective and do a definition, there is still another problem here. Uh, the so different devices being an input or output device is traditionally devices like a keyboard are our input devices, but that definition is not clear and cut at this moment. It's very blurry because it still is an input device for the most part in modern systems and modern keyboards, but you can always go in the market and find a keyboard with a display on it, and basically it becomes an output device too. There can be an argument saying that it's basically two different devices in one package, but yeah, I mean, the point of all this is the definitions are not that clear, and yeah, it has been evolving in the modern era. right? So, but what is the session about? It's about block devices, and that's what we're gonna use for the session when we talk about input output, right? So now we have established that there are a lot of IO devices, and we picked block device for this session. And why have we picked that? Because it is an interesting one, and it is interesting because there is a significant level of complexity involved with designing and developing a full stack for a block device, right? I mean, the number of layers of that stack required to be abstract, to be configurable, performant, consistent, all the while maintaining a very high level of data integrity and robustness makes it a big and feature-rich subsystem to study and discuss. And another reason to pick block devices that this is what we're here for, right? I mean, when we somebody says journey of an IO is basically we want to look into how that IO goes through the block device through different block device layers. Right, so let's first look into the entry point for our IO, and we're gonna use a very simple C program which opens a file and writes the buffer to it. Right, and to do that, we're gonna have a very simple open system call and then a write system call. Uh, we, we are defining a buffer of length 512 here. The relevance of the length of the characters here used would be discussed later, and we would see why we could have used a smaller one, but one of the variations that we're going to discuss later would fail and why that is. And so the open system call is a simple one where you send the path to the file that you want to open and the flags. Now what we're going to do is we are going to look into different variations of the open system call with respect to these two parameters, and we're going to look how and your IO is affected from that and the different paths that your IO will take depending on what parameters you pass to the open system call. Right. I would note one thing here is that we have emitted key definitions. From this C program is just a skeleton 3-line return value checks everything just to keep it simple and visible here in this small size slide, right? So, so this is the first layer that your IO goes through, right? When you do a write system call, it is goes to the system call layer, and the write is a very simple system call. It takes a buffer that you want to write and the length to be written from that buffer. And the simple layer, what it does, it basically calls into the next layer, which is VFS layer, and that is done through the function VFS underscore write. Right, and VFS stands for the virtual file system layer here. So we're going to discuss a little bit about the system call here. So the one of the key design points here for system call is that the interface is very simple, right? If you have an interface that you want people to call very frequently, and you want to keep it as simple as possible with as less number of parameters as possible, and uh, one of the significance of system call is that it's basically a communication. It's basically one of the ways user space programs can communicate and send and receive commands from the kernel layer, right? So next we're going to move to the virtual file system layer, right? So VFS stands for virtual file system. It provides a common set of interfaces for all the file system, and each file system defines its own VFS style functions. The VFS style functions are called file operation. They are defined using the structure file underscore operations. So the function that your IO move to was VFS underscore write, and depending on the file operation structure for the file system, underlying file system, it either calls the dot write function or the new sync write function, right? And what we're going to look into basically two different file operation structure in the subsequent slides, and for both of them, the path that your IO would take is new sync write function here. So that is what we're going to look at next, right? So the new underscore sync underscore write function first creates an IOV iter structure, which is IO vector iterator structure, and the buffer that you had passed to the write system call, that uh, it's the IOV iter structure. One of the parameters in that holds a pointer to your user buffer, and another one holds the count that you want to write, the number of characters, right? That which we send to the write system call. Once that is done, the control then passes on to the file system layer through the function call underscore write underscore iter. So this is the point when we start to look into the open system call and different variations we're gonna have, and how that affects your IO. Right. So first, what we're gonna do is we're gonna use the file path to a direct block device for the open system call. That is dev underscore dev slash SDA. Right. So that is the file name for the block device. And since we're using directly, there is no file system underneath it, uh, does not have any file system over it. The default file operation structure is used for it, right, which is def underscore block underscore fops, right? So from the VFS layer, the entry function for this file system is block dev write iter, or block dev read iter, depending on whether you make a write or a read system call respectively. So I would want to note again as that in this variation there's no file system involved, right? I mean, there is a default FOPS, but there are a few things that you would be missing if you use block devices like that. And block devices like this, the case of using block devices directly is done by modules and use cases like database or MD RAID, but from a user's perspective, you want a file system because there are a number of things that the file system provides, and number of features and convenience over writing directly to the block device, which we just saw, right? And it organizes data into files. It specifies conventions like maximum size of the name, the access permissions. It manages metadata like last access time, size of the file, and having a file system also provides a nice format for directory and file hierarchy, managing paths, etc. Right? So what we're gonna do is we're gonna move to our next variation, where we're gonna change the path to the block device to the path to a file in a mounted file system. Right, the name of the file being file underscore a, here being the first parameter. Right. So for the above call, depending on which file system the mounted directory has, depending on that, different file operation structure will be used, right? So for this example, let's take the ext4 file system and look into what happens when we use the above open call for opening the file, right? So for this, the write iter function that is defined, the entry point here would be ext4 file underscore write underscore iter, right? So, looking into the ext4 file underscore write underscore iter functions, we notice that there is a main the main code, what it does is there are three conditional branches there. Right, we're going to look into all the three branches here, and depending on a number of flags, your IO would either go to one of these branches. Let's look into the three conditional branches first. So first one is the code for DAX, which is stands for direct access, and it is part of the code added for persistent memory support. Right, I mean, one of the ways to access persistent memories is to memory map files to that memory region. I use it with general read and write system calls, and this is what is happening here. Right, this is not we are not going to be looking into this branch here because we are not really working with persistent memory here. Right, next is the buffered IO path. This path involves the page cache. So when data is to be written to a file, in general it usually does not get written to the disk directly where the file actually resides, right? Instead, the data is first written to an intermediate layer called the buffer cache, or the page cache as it is called nowadays. And for most IO, the system call returns from here, right? And later in the background, the buffers which has been written to, the dirty ones they are called, are written to their corresponding blocks in the file residing on the disk, right? So this is the buffered IO path, which involves the page cache. Right, next is the direct IO path, which basically skips the page cache layer. And these are the three conditional branches in the ext for file write iter function, and your IO would go to one of these depending on multiple things. So as I mentioned, the last two of the above flows is controlled by flags, and this is what we'll be looking into. So the relevant flags here for us is the o underscore sync and the o underscore direct flag, right? If we change our open system call here, keeping the file underscore a path, but adding these two flags to the second parameter, o underscore sync and o underscore direct, then what's going to happen? Let's first define what these flags are and what it controls. The o underscore direct flag controls whether the page cache layer is skipped or not, right? And once it skips, it gets directly written to the device below. However, the use of an O-direct flag can result in constraints on the size and location of user space buffers and IO file offset. The alignment requirements can differ depending on file system and kernel version used in Linux, and could even be non-existent at times, right? So, for example, the buffer length, this is a buffer length sent for IO to the IO system call read write should be a multiple of the physical sector size of the disk below, right? And if you recall, this is one of the reasons why we were using a character buffer of length 512. If we would have used something smaller, it would have worked for an open call which doesn't have O-direct, but for the ones that have O-direct, the IO could have failed. So next is the O-sync flag. This this controls when the read write call returns, right? And without the sync flag, the write call would return just after writing to the page cache, right, and the read both, and the flush would have happened in the background, right? Let's look into these flags one by one, and how your IO would behave if one of the flags is used, right? So for ext4, when you use the osync flag, it results in a call to ext4 sync file right after your buffer is written to the page cache, right? I would like to point out here is that this is the same ext4 sync file functions it's called which is called when fsync system call is called, And this is basically one of the preferred way of flushing the caches, and a lot of databases and other applications do this, where they perform an IO with or without sync, and they explicitly then call fsync, and this is one pattern that a lot of them follow. Right, so once the IO has from this ext4 sync file function, your IO passes. So right now we're going getting back to our code path, right? The journey that IO is taking. So from this ext4 sync file function, the control then passes to the file map function, and then it goes back to the ext4 subsystem through the function called ext4 underscore write pages. This is defined in the address space operation structure for ext4, which is called ext4 underscore aops. So through these functions of ext4, in the end, the control is then passed to the bio layer through submit bio, and this happens in the function called ext4 io submit. And the IO basically has moved from the file system layer to the next layer called the bio layer. We will soon look into what happens to IO in that layer. First, what we're going to do is we are going to look how your IO will behave if you use the odirect flag. And this is the third branch that we had discussed previously. So as I mentioned, with the odirect flag, your IO is going to skip the page cache, and what's going to happen is the control next moves to the number of IO map underscore dio underscore functions, like underscore read write underscore bio iter functions. Among them, one of the important ones is IO map underscore dio underscore bio iter function, which creates the bio. What it also does is it takes the user pages holding the buffer and pin them in memory so that direct IO can be performed on them. And one of the ways of doing that is through get user pages. Right, so just like the previous branch, here also the bio is then submitted using the submit bio function. So next we move on to the bio layer. So we have basically left the file system layer and moved on to the next one, where your IO has been moved to the through the submit bio function. This is a relatively small, simple layer, and it does do a small number of tasks, like whether the checking whether the block device uh, supports discard or not, whether it supports secure erase or not, a number of things like accounting for the number of bytes written, uh, throttling of IOs and things. Uh, but most it then passes the IO to the multi-queue layer through the function block mq submit bio, and this is the next function. What I'm going to point out here is that there is a reason why I'm not delving in a lot in detail in the bio layer, and I'm not going to be doing the same for multi-queue layer, is because we will be looking into these two layers in detail in our next subsequent sessions. Right, so next layer, as I mentioned, is the multi-queue block layer. Right, it is so named because it relies on two sets of queues named software and hardware queues. So a little bit of history here. Previous to, I think, 2.x kernel, some I don't remember the. So previous to that, there was just a single queue for process submission and processing of IOs, right? But as computer systems evolved, as they advanced and started, and multi-core systems and multi-CPU systems started becoming more and more popular. This basically, a single queue presented a bottleneck, and the change was made and this multi-queue block layer was introduced. As I mentioned, it has two queues, software queues, which are used for IO submission and are typically equal to the number of CPUs in the system, and the hardware queues, which are used to submit the IOs to the underlying device. So the hardware queues are usually equal to the number of queues or parallel processing units in of the underlying device. What I also would like to mention here is that these two parameters are configurable by the device driver, which is using initializing and using the multi-queue block layer. We will be seeing one of those examples later in the session. Right, so this is a very simple depiction of the multi-queue block layer, where we see that the IOs are submitted from the bio layer, and there are a number of software staging queues, which is, as I mentioned, is equal to the number of software queues at times. And next is the hardware dispatch queues, which is directly dispatching the requests to the device driver below. There are a number of variations here that happens when let's suppose the number of software queues are more than the number of hardware queues. Then what happens is more than one gets allotted to the same hardware queue. If if there are more hardware queues than the number of software queues, then a round robin order is followed, and if there's one to one, if they're equal, then there is a one to one mapping of these. Right, so any device so multi-queue block layer is designed in a way which allows any device driver code to hook into its API and start using the request-based queue submission and completion mechanism, right? So there are a number of simple steps which are to be followed to use the multi-queue block layer. These there are obviously ways of fine-tuning and configuration of the parameters, as I mentioned before. Right, so the multi-queue block layer initialization API uses a structure called block MQ tag set for initialization. This structure is a way of communicating your custom driver related information to the MQBL. It contains information about the number of hardware and software queues, as I mentioned, command size, and so on. It also basically contains a pointer to the structure block MQOps, which contains function pointers to your custom functions, which will be called in the from the multi-queue block layer code. Right, so we will see the essential ones from these functions in a moment. Right, so once the block MQ tag set params is initialized with the relevant data, the function block MQ alloc tag set can be called with the structure. So the second step, the last step here, is to initialize the request queue structure, which is one of the main structures in MQBL. It will be used internally by the MQBL to access the custom function pointers. Besides that, it also holds a lot of MQBL related data fields. So as I mentioned, the block MQ tag structure also contains the block MQ ops structure, which the device driver can set, and this ops structure contains essential functions, which is which must be defined, which is QRQ, which is used to submit the command to your underlying device, and map queues, and completion, which is used to complete the requests. So this Q, RQ, and complete are the entry and exit points for device drivers, respectively. Right. So the I/O after the MQBL is passed on to the device driver layer through the QRQ function. Right. Now, in order to look into this next stage through which the I/O goes, we have to pick one device driver. Right, we have a number of device drivers which uses this hook, right? I mean, There are older legacy ones like SCSI, network related ones like NBD, or newer ones like NVMe PCI. Right, we're gonna look into the NVMe driver here and see how it handles the I/O. Right. So what you would notice is during in NVMe during the block MQ tags and init phase, it uses the NVMe MQ op structure. So this has the .qrq and .complete functions defined. One more thing to note here is that NVMe also sets the number of hardware queues to the number of online queues for the underlying NVMe device control structure. And this is the point that I was conveying previously, that the device driver can control the parameters for NVMe. Once this block MQ tag set init phase is done, it's gonna look like this, where the hardware dispatch queues has a one-to-one mapping to the submission queues of the NVMe controller. Right, so the entry function for the NVMe PCI driver from the MQBL multi-queue block layer is NVMe QRQ. This is the function which is defined in .qrq in the ops structure. So it's the function does some preparation through NVMe prep request, like setting up the command, which is done through NVMe setup command, and then calling block MQ start request, which notifies the block layer that a request is going to be processed now. It then copies the request to its submission queue. So one more thing to note here is NVMe operates on separate submission and completion queues. So once the IOs are submitted to the submission queue, the request is submitted there. This is the point where the IO would be picked up by the device and then written to the physical medium. So this is the point where we stop, and we basically jump back to the completion path, which is a point which returns when the underlying hardware device has done the writing to the actual sectors. Right, so for the completion of NVMe PCI, we again look back to the NVMe MQOP structure, where the .complete function is defined, which is pointing to NVMe PCI complete request. It is a small and simple function which first performs the unmap and calls NVMe complete RQ. NVMe complete RQ then checks the status of the command, and depending on the status, if the command has passed, if the IO was successful, it calls NVMe end request. The NVMe end request function then calls block MQ end request, which moves the control back to the block MQ layer. Coming back to the block MQ layer, this block MQ end request function frees up the requests, and then does some small processing, like it decreasing the usage reference count to the request queue structure. Basically, this completes the journey of our IO, and this is where we stop. We are an educational, free-for-all non-profit organization. You can reach out to us from the below email, follow us on LinkedIn and YouTube. We are also planning to have a blog website where we're going to post everything that every material that we use to create the videos, in written and the notes and a lot more in the future. So thank you for watching.